Good evening, Bearcats. Hope you had a great Thanksgiving, and a big shout out to Kevin and Melvin for that wonderful drum roll they've sent me. Now they can help me figure out how to interject it in the right places. Hope you all had a great Turkey Day, and I hope that I see you back safe and sound in the morning. Okay, we're going to go over some application stuff tonight. This is about growth and decay models, and this is kind of a new thing and a little different than your textbook, so you really want to take some good notes. And the examples used here will be, you can use those examples to answer the applications on the review or the pre-assessment that we're going to have, and then they will also model and help you with the application problems on your test Friday. Remember, we start trig on Wednesday, so that's exciting, and let's go ahead and get started for the evening. Okay, the first thing I want to talk about are these growth and decay models, and we're going to talk first about finances. We have a formula here, Q equals Q sub O B to the T, or Q sub 0 B to the T. Q is the amount of at time T, whenever time has passed, is the final amount we're looking for. Q sub 0 is the initial amount, the beginning amount. B is the 1 plus the growth rate. So if it's just an annual growth rate, it's going to be 1 plus the percentage if we're talking about finances. And T is the time in years. And those time in years can be time in the future and time in the past. And that's kind of something new that we haven't done before. So let's take a look at this example. This example, and I'll try to leave that little formula up there for you. Suppose that the cost of a BMW sedan increases at 1.5% per year, and if the cost is now $85,000, what will it be 5 years from now? And we want to know also what the cost was 5 years ago. All right, well, the first thing I see is that $85,000 is our Q sub 0. That's our initial amount, so that's our Q sub 0 amount. The next thing I see is this 1.5%. In all of these problems, you must change your percentages to a decimal. So like the Beyonce song says, go to the left, and this would now be as a decimal 0.015, and that's really an important thing that we need to know. And of course, T will be time in years, 5 years from now, and T 5 years ago will be a negative 5. And that's something I don't know that we have done before. So plugging into our little formula here, we want to know the amount after time. So Q equals, our Q sub O is 85,000. And we have B, which is 1 plus the growth rate, so 1 plus the 0.015. And it will be raised to 5 years. Then we also are going to have Q equals 85,000, 1 plus the growth rate. But we're going to go back 5 years, so minus 5 or negative 5 for T. In the first case, we will get approximately $91,569.10. And 5 years ago, our BMW was worth approximately $78,902.13. Okay, let's move on to the next example. That one's pretty easy. Next, we want to talk about a little, I guess, manipulation of that same type of formula. Y now is the amount after time has passed. This is used for exponential growth and decay models and is expected for every calculus student to know and understand its proof. C is the initial quantity. That's the same as the Q sub 0. E, of course, is our constant, and we can approximate that at 2.72, but actually you'll use the calculator for these problems. And then K is our proportionality constant. That's sort of in place of our B. And there's a little formula or a proof that we're going to look at for K. And T is time again. If K is greater than 0, of course, we'll have growth, and if it's less than 0, we'll have decay. Here is the part that you really need to focus on in terms of K. What K is. K is really equal to 1 over the change in time, okay, so our change in time if we have information about what has occurred already over time, and times the natural log of the quantity, the second quantity over the initial quantity, or the quantity after the next quantity after our initial quantity. So that is our little formula. We're going to be using that for the next several problems, and hopefully with practice this will seem pretty easy to you. It is a big shortcut, and I think that you will like it. So let's move on to our first example. You may want to pause at this point and of course write all of this down so that you will have all your notes. Okay, let's take a look at this example here. I've written the formulas at the top and the little formula for K that you have to learn. Suppose that we have 10 grams of plutonium isotope, Pu-239, and this is released in the Chernobyl nuclear accident. We want to find out how long, so we're looking for time, it will take for 10 grams to decay to 1 gram. One thing I did not put on here, a little note, that plutonium half-life, the half-life for plutonium, is 24,100. All right, let's see what information we have. We have information about time and our amounts. Remember, our quantities and our time is what we're looking for. So let's take a look at what we have. We have time and we have quantities, or the amount. So we know that at 0 time we release 10 grams. And then we want to know how long it's going to take for the 10 grams to decay to 1 gram. So we don't know the time it's going to take to get to 1 gram. But we do know the half-life. So we do know that that amount will reach 5 grams at 24,100. 24,100. So this is what we'll be looking for, but the other two pieces of information is what we have. So we can use what we have to find our the time to get to 1 gram, to reach 1 gram. It's probably going to be quite a number of years since 24,000 is the half-life, and we want to get down to 1 gram. All right, so let's take a look at this. We know that our amount that we want to reach is 1. We know that our initial amount was 10. Let's go over here and calculate our K value. We're going to be using our K, so we have E. Let's calculate our K value. So remember, K would be 1 over the change in time. Well, the change in time for us would be from 0 to 24,100 years, so 24,100. And then it would be ln, and it would be the quantity after the first amount, which we have information about, which would be 5 over 10. Interesting. 5 over 10 becomes 1/2. I believe, because this is half-life, so think about that. And so there's our K value, and then we're going to be solving for T. So I'm going to plug this in, so it'll be E, and I'm just going to plug it all in, write it all in, and that's what I expect you to do on your test. So 1 over 24,100 ln, oops, sorry, that's not very pretty, ln 1/2. And then we will solve for T. We will solve for T. All right, so let's go ahead and start doing that. I'm going to rewrite this so we can go ahead and do our work. So I'm going to say 10 e raised to the 1 over 24,100 ln 1/2 times T. And of course that equals 1. The very first thing we would do would be divide by 10 on both sides, and we would have e raised to the 1 over 24,100 ln 1/2 times T equals 1/10. The next thing was we're stuck in an exponential equation, so we would need natural logarithms, and so we would ln both sides, and we would have ln 1/10 is equal to 1 over 24,100 ln 1/2 T. And so our answer then is going to be for T, if we solve for T, we're going to have ln 1/10 divided by 1 over 24,100 ln 1 half. ln 1 half. And once you put all that in the calculator, and that's the part I really want you to practice in class to make sure you're entering all this information correctly in the calculator. You do need to show all of this work. I need to see all of your steps. Do not round anything into the end. And once you put in there, you should get 80,059 years, or approximately. Go Bearcats. A lot of years. Don't think I'll be around. All right, let's take... Okay, so in this example, suppose an exponential population of fruit flies is increasing according to the law of exponential growth. There are 100 flies after the second day of the experiment and 300 flies. Oops. 100 flies after the second day of the experiment and 300 flies after the fourth day of the experiment. We want to approximate how many flies were in the original population. Okay, we're going to use this same little piece of information. Let's set up what we know. We don't know. We know at time 0 we don't know what the original population was. That's what we're looking for. So this is what we're going to look for. This will be the answer we're trying to get. We do know that after 2 days we had 100 fruit flies, and we know after 4 days we had 300 fruit flies. So if we're following the law of exponential growth, we need to find our proportionality constant. And so to do that, we're going to find K. So let's go and find our value of K. So K would equal, and we're going to use this information right here, would equal 1 over the change in time. So 1 over 4 minus 2 would be 2, so 1/2 ln, and that would be equal to quantity, the second quantity, which would be the 300 over the 100, and 300 over the 100 would just give us 3. So our constant K then would be ln 3 basically over 2, or 1/2 ln 3. All right. So now we know the value of K. We can go back and use these first two pieces of information to find our answer. So we know that over 2 days time that our output is 100. So we know that Y would be 100. What we don't know is our initial quantity. So we don't know C. But we know that the output is 100 when we raise E to the K, which we now know to be 1/2 ln 3, and times time, and we know that 2 days have passed. So when we get ready to solve this, we're going to have C is equal to 100 over E raised to the 1/2 ln 3 times 2. And when we figure that out, we're going to get approximately 33.3, or approximately 33 flies in our original population. All right, let's go on to the next example. Okay, this will be our final example for the evening. This is about a business problem. 4 months ago, after it stopped advertising, a manufacturer company noticed that its sales had dropped 100,000 units per month to 80,000 units per month. So only the sales were dropping after its advertising, so the advertising apparently was helping a little bit because the sales were dropping by less per month. If the sales follow an exponential decline, but they are continuing to drop, what will they be after 2 more months? So the sales are going to continue to drop. It's just they're dropping at a lesser rate after some advertising. That's how I read this. All right, so let's take a look, and using our formula again, let's see what we have. We know that at 0 time, we're going to consider our initial time, the sales were dropping by 100,000 units. We know that 4 months later, they had dropped to $80,000 per month. I guess that's really how this reads. The sales were 100 and now they're 4 months later they're down to 80. And now what we want to know is what will happen after 2 more months. So from the 0 months to 2 more months after the 4, that would make us at 6 months. What would be our sales? What would be our sales? Okay, once again, let's go ahead and set up K using this information. So K would be 1 over the change in time. And sometimes we write this as 1 over delta T for change in time, by the way. You'll see that sometimes, so that's important to know. So 1 over the change in time, which would be 1 over, and we would have 4 minus 0 or 4. And then we would have ln, and we would have the 80,000 over the 100,000. So 80,000 over the 100,000. Of course, all these zeros can go out. We have 8 over 10, which reduces to 4 over 5. So it equals 1/4 ln 4/5. And that's our K value. So now what we want to do is when time is 6, when T is 6, we want to find out what our output is. And we already know our initial value, the C value was 100,000. So we can just plug on into our formula. So we have Y equals, and our initial amount was 100,000. And we know it's going to be E raised to the 1/4 ln 4/5. And we know that the time now would be 6. When we get ready to plug all this in our calculator, do so very carefully, and your amount will be approximately, your sales will be approximately $71,554.18. Okay, go Bearcats. Hopefully this makes sense. We'll talk a little bit about it more in class, and there will be some on a pre-assessment that you can use this information to solve. If you understand this, it makes solving these application problems very quick and easy. All right, have a good night, and go Bearcats!